Okay, and see. Okay, cool. All right. Okay, class. Hey, all right. We're going to go over the 2020 AP Physics review number 4. These are solutions for momentum. And now, before we start here, here's some ideas that, in case we forgot, the main topics of momentum. Okay, so let me go ahead and get this annotation here. Okay. All right, let's kind of put this up at the top here. Okay, so remember now, so conservation momentum is a fundamental law. This is always true for any type of collisions, right? And some of the momentum before a collision always equals after a collision, okay? And so we might have like here's M1, right? And it might be going in this direction like this. And here's another object, M2, right? And it's going that way, and they're going to collide. Okay, so here you have, and remember, these are vector quantities. Now, for purposes of this, I would make going to the right positive. Okay, make that positive, okay, just to help us out. And that way, and going to the left is negative. Okay, that's going to help us. Okay, all right. So you have M1 V1 plus M2 V2 equals M1 V1 prime, which means after the collision, plus M2 V2 prime after the collision. Now, there's several kinds of collisions. One is called elastic collision. For this to be true, kinetic energy before must equal kinetic energy after. So essentially, if the initial speed equals the speed after, then we know it's an elastic collision. Okay? If the velocities are the same, then it's going to be elastic collision, assuming the mass stays the same. Okay? Then we have inelastic collision, means that kinetic energy is not conserved. Okay, and it's either perfectly inelastic, where they stick together, right, or it's an explosion. Okay, where zero before, and you have something that's together like this, and then afterwards it kind of breaks apart. Kind of breaks apart, kind of like this goes that way, uh, and this object goes that way. You have an explosion, right? It blows up. So this would be an explosion. Okay, so these are some things we want to kind of remember here. Okay, in case we forgot. Okay, so this is always true. Okay, all right. So let me go ahead and clear this real quick here, and also I'll post this video too, so we can see it later. Impulse, okay, here's impulse, okay, and I think we did a lab here. Remember this lab where we had this box like this, right? And this was a box here like this, and we had a cart, right? We had a cart like this, and uh, the cart went like this here, and the cart had some mass like that, then it struck the box, right? Remember, it struck the box, and then it bounced backwards like this, it bounced back like that, and we have this here, and bounce backwards. Here's M. Okay, so what happened was that going to the right is positive, going to the left is negative, right? So we want to be careful about that. And remember our graph, we had a graph that could have been a rectangle, or could have been a triangle. So what happens is that here's force and delta T. So the area under the curve is impulse with a J, called a jerk, okay? And so what happens is that impulse J equals change in momentum, which is equal to force times delta T, okay? It also equals mv minus v. Now here's where we want to be careful here because of the, watch negative signs, okay? Now if something rebounds, okay, that means that this is going to be negative, right? Okay, the final velocity is negative. When it bounces off here, what's the final velocity? It's negative, right? And the initial velocity is positive. So you have negative minus, and so if something bounces off, the impulse is greater. Is the worst kind of situation, is when you have a collision and there's a rebound effect. Okay, that's the most impulse that you'll ever see. Okay, and okay, and then we had the ballistic pendulum, right? We had this where we had this block here, and here's a mass. It lodged into here, then it went up some angle here, and this was M plus big M, and this was delta H, and delta H was right here, and we had delta H was equal to L parenthesis 1 minus cosine of theta, which is right here. Okay? And so what happened was that when we do this equation here, remember this is equal to 0 because this block is not moving initially, and when it collides, when it's stuck like this, it's v prime m plus big M, right? Like so here. Okay, and okay, and then okay, so that's the momentum part, and then kinetic energy we have here. So we have 1/2 here, right? And it's going to be okay. Now it's the kinetic energy of this whole thing right here. So that means it's going to be was it m1 plus was it m2, right? M2 and v prime was it squared, okay, has to equal mgh, m1 plus m2, like so, and g times h. Okay, so if we know what h is, then we can plug it in. But if we're given the angle theta, then we have to use this relationship here for h. And so this is for the ballistic pendulum. There's a simulation for that that you might want to practice on or kind of work on there. So this is a ballistic pendulum. Okay. And let me go ahead and let's go ahead and kind of clear this real quick here. Clear drawings, and let's go ahead and go down. Okay. And also another thing here we should worry about is when this thing swings. So if you have a pendulum swinging, simple harmonic motion only occurs when theta is less than 15 degrees for very small angles, right? And period is equal to 1 over frequency. And in case we need to, period is equal to 2 pi times the square root of L divided by G. Okay, and then remember, here's amplitude, here's a crest, and if you go like that, that's one period here. It's also one wavelength, and just some things to kind of be aware of. All right, let me go ahead and hit pause here real quick, and let me let's pause real quick here. Zoom recording here. Okay, so so here's trial A, trial B, and trial C. Anybody have any questions about trial A, B, or C, or how we would respond to this? Okay, so it looks like okay, pretty good. So again here, trial A, inelastic collision because they kind of stop and stick together. Okay. Trial 2, they exchange velocities. So the velocities before the collision equal after the collision. Therefore, kinetic energy is conserved. And then in trial C, they collide, but they bounce back slower, which means kinetic energy was lost, usually in the form of heat, sound, or deformation. Okay, so let me go ahead and hit pause here real quick. Okay, all right, so here we have this tether ball going around in a circle here, okay? And so a couple of viewpoints we want to take a look at here is, let me take a look at this here, okay? So here is a edge-on view of what happens. So I'm looking at the ball here, and this is the angle it makes if I'm looking at it at another angle here. Okay, so it's going in a circle. So it says here, 2 students are playing a game called tetherball, where a ball is connected to a rope on the top of a vertical pole so they can move around the pole as shown in the figure. Number A, as the ball passes directly in front of the pole such that it is moving to the right, it collides head-on with a small mass thrown at it softly by a 3rd student. In a clear, coherent paragraph-length response, describe the motion of the ball attached to the rope after the collision compared to the motion before the collision. So okay, so some thoughts here. Okay, now am I recording still? Let me double check here. Hold on. Okay, make sure I am recording. Let's see.
Yeah, you're still recording.
Oh, okay.
Yeah, you just stopped the screen share though, so
Oh,
you have to
geez. Okay, hold
share
on.
it again.
Okay, gosh dang. Okay, hold on. Share screen. Number two, let's go back to here. Okay, there we go. Okay, still recording, right? Let me see if we're, yeah, still recording. Okay, all right. So, okay, so some thoughts here to think about as we do this. Okay, let me go ahead and put this up here a little bit. Okay, okay. So head-on collision. Now, when it's head-on collision, that means that it's kind of like it's kind of like cars on a track. It does that. Okay. Now, if it was at an angle, it would cause directional change, but it's just head-on, so it does that kind of thing. Okay. So no direction change. Conservation of momentum still applies, and it's going to be an inelastic collision. Okay, ball has horizontal velocity VO to the right. Collision will change the speed, but not direction. Okay, now if we need to, here's some stuff with centripetal force. Okay, Beta and Emma, we just talked about centripetal force here, mv squared over r. If we need it, it's here. So some of the forces in the x direction, we have tension. Okay, so just some things to think about here if we need to. In the y direction, we have mg. A force of tension is equal to mg, just in case we need to think about that. Okay, and theta is with respect to the pole. Okay, so one way we should answer this question is the ball has initial velocity in the x direction going right. And inelastic collision results with the ball losing kinetic energy, causing a decrease in speed. As a result, centripetal force also decreases, causing less tension in the rope. Okay, the angle with respect to the pole decreases as well. The force of gravity is balanced by the vertical component of tension. Okay, so we go ahead and hit pause here. And okay, all right, so part B here. At another time, as the ball passes directly in front of the pole, such that it is moving to the right, it collides head-on and sticks to a small lump of clay. So it's going this way. Here's a lump of clay. It sticks onto it, and it sticks together. So this would be a perfectly inelastic collision. Okay, just kind of think about that. Okay, thrown at it softly by a third student. The rope breaks at the same instant the clay collides with the ball. Describe the motion of the clay system after the collision compared to the motion of the ball before the collision. All right, so a couple of things here to think about. I have this here. Okay, now if this is going in a circle like this, if I break the string, what's going to happen to this? It's just going to go in a straight motion, right? So if this is swinging around like this, all of a sudden the string breaks. This is going to do projectile motion. Okay, so as the string breaks, it's going to do projectile motion. Okay, just kind of think about that. If I'm going like this and I let it go, so it goes straight, and then it's going to eventually become projectile motion. What's that?
Oh, I was just saying, yeah.
Okay, all right. Okay, so some thoughts here. Total inelastic collision. Therefore, kinetic energy changes, right? So the velocity of the tether ball before and after, it was going to slow down after because it's an inelastic collision. Velocity decreases. The string breaks. Therefore, centripetal force is gone. Okay, so after the string breaks, the ball becomes projectile motion. Okay, now velocity in the x direction stays constant, right? So here's remember now here's the ball like right here. Okay, so initially it has VOX here. It has velocity in the x direction here. Okay, then it's going to take projectile motion, kind of like this, right? And each time VOX is going to stay the same in the x direction. However, as it goes down, the y component of velocity is going to increase each moment, right? As it gets closer and closer to the ground, and so on and so forth. Okay. So what we could say is that the clay impacts a tether ball moving horizontally to the right. The collision is head-on and results in a perfectly inelastic collision. Since kinetic energy is not conserved, the ball clay system's velocity decreases in the horizontal direction. At the moment the string breaks, centripetal force is no longer maintained. The ball clay becomes a projectile motion with constant horizontal velocity and increasing vertical speed until impact. Okay, wow, a lot of stuff there. So let me go ahead and hit pause here, and we'll go ahead and pause. Okay, all right. So question 3 is a QQT, 25 minutes. Okay, and let's look at the problem here. We have an arrow going into a pumpkin. Okay, and so what happens is that in one case, the arrow. Okay, there's 3 scenarios. The first scenario, the arrow hits the pumpkin and bounces backwards, okay? Or hits the arrow and bounces back. That's scenario 1. Scenario 2, it lodges into the pumpkin, okay? Then the third one, it goes through the pumpkin. Okay, so do we see the 3 scenarios? Those are the 3 different things that are going to happen in this problem, okay? All right, so, okay, so the arrows are made with the same material, okay? Now, there's embedded arrow, which strikes the pumpkin and remains embedded, okay? It's going to swing. The pumpkin is going to swing upwards. So do you guys agree that in all 3 scenarios, is the pumpkin going to move up kind of like kind of this kind of a situation here? Okay.
Yeah.
Yeah. So here's theta, okay? So in 3 scenarios, it's going to do this. Question is asking which one's going to be the greatest angle, okay? So the embedded arrow strikes the pumpkin, remains embedded. The passing arrow passes all the way through the pumpkin and continues traveling away from the archer while pumpkin swings to a new angle. Okay. Bounced arrow that bounces off the pumpkin back toward the archer while the pumpkin swings to a new angle. Okay, so now, so it says here in number 1, rank the 3 angles, theta embedded, theta passing, and theta bouncing from greatest to the least. Okay, greatest to least here. Okay, now, okay, so some things here to think about. Okay, ballistic pendulum is one thing. We're going to use conservation of energy or conservation of momentum. Perfectly inelastic collision. We have conservation of energy, conservation of momentum. So a lot of things going on here. Okay, now this is the ballistic pendulum here. I did a thing here for us here. Where we got here? Ballistic pendulum. C. Oh, is that? Oh, that's answer. That's answer C. Hold on, my bad. I got backwards. That's C. 1D. 1C. 2B. Let's see what we got here. Here's C, 2B. Okay, 3. Okay, where's 3A okay. We say there's D. There's C. Okay. Let's see. Where did it go here? Hold on. Let me go back up here. Let me stop recording real quick here. Let's. All right. So this is going to be 3A here. So here's 3A. Okay. So this is going to be theta embedded. Okay. I'll do E for embedded here. Okay. And then we have this here, and we have theta. Was it passing through? Okay. Theta passing. Okay. And then we have theta, and we have your bounce, theta bounce. Okay. All right. So what it should be is that the bounce is going to be number 1. It's going to have the greatest angle. Okay. Number 2 is going to be the embedded. And then number 3 is going to be a passing. Okay. All right. Cool. All right. Now, what I'll do is I'm going to show you now they want, okay, you can do qualitatively or equation-wise. Okay, so there's the answers. Anybody have, okay, initially here, before we give the explanations, anybody have any questions about, or did anybody get this right? 1, 2, 3, 1?
Not in my initial thoughts. I thought it'd go the bounce. I haven't actually done them. I haven't had time to.
Okay, sure. Okay. Now remember.
My initial thoughts though. And just thinking about conservation of energy and stuff like that, wouldn't it go? I haven't figured out the difference between passing and the bullet in my brain and bouncing off.
Okay,
But then launching, wouldn't that one be the greatest because the most amount of energy is transferred into it, which would be a greater velocity?
oh no, bouncing is the worst case. Any kind of collision, you never want to bounce. Anytime, remember bouncing, remember now you have the double
Because
negative.
you have the negative.
It's going to increase the impulse. Okay, so, okay, yeah. So let me,
Wait, what's the order again? Sorry, is
Yeah.
it from greatest to least
yeah, it's greatest to least. So the greatest one is going to be the bouncing one. Okay,
for the theta?
okay. The second one is going to be embedded.
Oh, would that be because when
Yeah.
it bounces, you have a negative velocity, so you'd have to have a greater velocity of the pumpkin?
Yeah, yeah. Well, because you have a negative. Yeah. So, yeah. Remember now. Okay. Well.
Okay, I think
Yeah. Impulse. Remember. Okay. Remember now. Okay. Remember, in all these problems here, going to the right is going to be positive, right? Going to the left is negative. Okay. Now, just before we get into the here, here's M, right? And this is going to be V minus VO. Okay. So VO is positive. So VO is positive initially, right? And then final velocity is negative. So you have negative. So this is a additive effect, right? So that's going to be the greatest situation here. Okay. That's going to impart the greatest speed onto the pumpkin. It'll go to the highest angle if something bounces off. Okay. So bouncing off is the imparts the greatest momentum is bouncing off.
yeah, I just had that realization.
Okay, now before we get into words, because I think if we look at the equations, that might explain things a little bit better than if we were to do it the other way here. So hold on here. Yeah, let me take a look at. Okay, so now so let me hit clear real quick here. Let me hit clear. Okay, so everybody's good on the order, right? Okay, so let's take a look at y. Okay. And I think personally, mathematically explaining it is easier to see, and then we can discuss how we would say it in words. Okay. All right. So let's go to, let me make this a little bit smaller here. Okay, like this. Oh no, that's bigger. Let's go smaller. Okay, right here. Okay. All right. So here's the bounce. Okay. And let me make it, okay, here's the bounce. Okay. Make it a little smaller. Okay, everyone can see this here? All right, so bounce, right? So let's just do conservation of momentum. Okay, so initially the pumpkin's at rest, right? Right here, okay? So this is MA, VA, mass of the arrow, velocity of the arrow, okay? And initially VA is positive, right? Okay, after the collision, VA is negative, right? And the pumpkin is continuing on to the right. So the pumpkin's velocity is also positive after the collision, okay? So if I solve for VP, I want to solve for the velocity of the pumpkin. If I do that, I get this expression here for the velocity of the pumpkin afterwards. And if I look closely here, see how these are additive here? Okay, they're additive, okay? So if you want to make all the values 1. It makes it easier to calculate if you need to, okay? Now, the embedded situation, okay, embedded. So again here, mass of the arrow, velocity of the arrow. Mass of the pumpkin, velocity of pumpkin is 0. It's embedded, so it's inelastic collision. So that means that mass of the arrow plus mass of the pumpkin and V prime. So V prime is also the velocity of the pumpkin. So if I solve for V prime, I get MA VA over MA plus MP. Compare these two results here. Would this be greater than this? Right?
No.
If you look closely, if they're all, yeah, this is a bigger denominator.
Yeah, no, that the one that bounces would be larger.
Yeah,
because yeah.
Yeah, 'cause it's
Okay.
divided by a smaller number.
Yeah, good point. Good. Yeah. Okay. Now, look at the third case now, right? So let me go ahead. Let me hit clear. Okay. Now, the third case it passes through, right? Okay, it passes through. Okay. So let's go here with passes through. So it passes through, again, mass of the arrow, velocity of the arrow. Okay, this is positive again, right? This is positive. Okay, velocity of pumpkin is 0. So now here's mass of the arrow, velocity of the arrow. This is positive. Okay, mass of the pumpkin, velocity of the pumpkin. That's also positive, right? So when I solve for, I want to solve for this, velocity of the pumpkin. when I solve for velocity of the pumpkin, what happens here? MAVA minus. See how this is minus, and this up here is, hey, Eddie, this up here is positive. Dog here, okay. Eddie, you okay, man? Okay, positive, okay. And here's MP. So now, comparing all three of the results here, we can see that this one here would be like what, number one, right? This would be number two, and this would be the third. Okay, this would be the greatest displacement. Greatest displacement comes from the greatest velocity after the impact. This would be number one, this would be number two, this would be number three. So what you would need to do is take this idea and kind of put it into a sentence or two, explaining this idea here. Okay. Is that kind of, should we go over the explanations, or do you guys kind of see using this idea here, we'd want to now construct some couple sentences about each of them, explaining how you would explain this in a sentence here. Okay, so,
I think if you put it into words, that would help with the test.
okay. So ballistic pendulum, we're going to use the conservation of momentum, perfectly inelastic collision, conservation of energy. So the first part, conservation of momentum. Okay, here it is right here. This is the equation here. Then we're going to use the conservation of energy. Kinetic energy initial plus potential energy equals kinetic energy final plus potential energy final. So the initial kinetic energy is going to be 1/2 ma plus mv v prime squared. So, okay, make sure we got this understood. Okay, since it's at the initial position, or delta H is 0. So therefore, potential energy is going to be 0. After the collision, kinetic energy is going to be 0 because it comes to rest. And we have here potential energy final, which will be mgh, in this case, ma plus mp of the pumpkin, that's the final mass, times g and times h. Now, delta h, if we can measure h, then we're good. If not, we have to remember that h is equal to L parenthesis 1 minus cosine of theta embedded. Now, what do we have to measure to do this experiment? We have to measure mass of the arrow, mass of the pumpkin, length of the pendulum, and also the angle, embedded angle. This is what we have to measure. Okay, now if you don't say this, then you might get marked down. You want to make sure we have to measure these. Okay, and then scroll down here to show our necessary calculations here. Okay, so we have here, so velocity of the arrow, mass of the arrow equals ma plus mpv prime. Okay, and this is from conservation of momentum. Conservation of energy is 1/2 ma plus mp times v prime squared equals ma plus mpg. I substituted this into h here, so substitute this into h. We have L 1 minus cosine embedded. Then solve equation 1 for v prime and substitute into equation 2 so VA can be solved and calculated. And that's what we would need to do. In fact, you probably want to, on the simulation number 4 is the ballistic pendulum. So you may want to use this step here to solve for that and just kind of, write an outline or procedure on how you would do that. Okay. All right. Let me hit erase here. Let's clear everything here. So that would be question 3. Okay. Question 1D. Okay, we're almost done here. Okay, so question 1D. Okay, let me go back up here again. Let's, where's it at? Okay, so 1D. Okay, and we'll be almost done here. 1D, the pumpkin with the embedded arrow begins to swing back and forth. How could the frequency of the swing be determined? Ignore friction. Okay, so we would measure the period, right, for several oscillations. Take the average and use frequency as 1 over the period. And make sure that the embedded angle should be under 15 degrees so we can use simple harmonic motion. Okay. So remember the period, if I start here, I need the swing to go here and back again. And that's how we could determine the frequency there. Okay. Okay. And then E here, last one, a student claims that the conservation of energy has been violated because the pumpkin and arrow system eventually comes to rest. Explain why the student would appear to be correct and how you could correct the interpretation, and how you could interpret how you could correct the interpretation. All right, so E here, conservation of energy. Energy cannot be created or destroyed, just transferred to a different form. Without considering frictional heat loss, the student observed the incomplete transfer of potential to kinetic, kinetic to potential, potential back to kinetic. However, on each swing, some kinetic energy is transferred to both potential energy and heat. Okay, so the full equation is that we have to consider frictional loss. Okay, so eventually all the kinetic energy is transferred to heat. The pendulum pumpkin system comes to rest as there is no more potential energy left. Okay, let me go and hit pause here.